So last class period, I introduced current and talked about capacitors. And I didn't get to Ohm's Law. That's the topic today. That's why I have to do some lecture first. So the lab guide has all of the information you need on the topic, to be honest. And we start off with just, well, what is current? Do you remember current from yesterday? Flow of charge, right? And I pointed out that since Ben Franklin randomly decided that whatever was on the amber was going to be negative, and it's electrons that are on amber, because amber in Greek is electron, that we have negative particles flowing to make our current. And so in physics, we talk about conventional current. That's the name that's given to it. And the conventional current is the flow of positive charge. In fact, if you're talking about a wire, there is no flow of positive charge. It's a flow of negative charge in the opposite direction to the current. Now, just to make me as a physicist feel a little better, I will point out that if you have something like an ionized gas, you do have positive charge carriers then. And in some semiconductors, you have what appears to be a positive charge carrier, although when you get to studying it, we call it a hole. It's a positively charged hole. But what's a positively charged hole? It's a missing electron. And so in semiconductors, they'll talk about hole migration as positive charge flow, when in fact, it's electrons leapfrogging the other direction. So when we talk about this current flow, to understand how electric circuits work, the first thing to know is that word circuit. Circuit means that you start and end at the same place. So everything we do in electric circuits, we need to have a completed circuit so it's going around in circle, circle after circle after circle. And so this picture shows two different circuits. The one on the left is an electric circuit. And that electric circuit is drawn with conventional looking devices, not with our arcane physics/engineering symbols. And so it shows a DC voltage source. That's what you're going to use today, a DC voltage source. You're not using batteries because batteries are electrochemical cells. You're giving energy to charge using a chemical reaction. What we're using today is just going to take electricity and use that electricity to give you electricity. It's not using a chemical reaction. So it's a DC voltage cell as shown here. And so it has a positive side and a negative side. Notice this here, it's showing electron flow. It's not showing conventional current, it's showing electron current. And I know when I was teaching at PUC, there was somebody in our, it wasn't engineering, it was a engineering technology or something like that, who was very adamant that we physicists were wrong and it should be electron current. And so, he would love this. Me, not so much. So we have electrons flowing out of which side of the power supply? Should electrons leave the positive or the negative? Electrons are repelled by negative. So the electrons should be leaving the negative side here. And so the positive is in red, the negative, and this is in blue. In most things, the negative is black. So if you look at your power supply we're using, it has two outputs, and one is red and one is black. The red one is positive. The black one is actually ground. So the electrons go out of there and they come to the light bulb. And when the electrons go through the light bulb, they have a resistor. And it's named a resistor for the simple reason that it resists charge going through it. And so I always like to liken this to when I was in graduate school, I always wanted to be a football player, right? But going to Seventh-day Adventist institutions, there's no football to be played. I was a varsity flag football player. Yeah. So, our varsity team practiced like every night, and then we played 2 games the entire season. One at PUC and one PUC at Lowell Linda. Anyhow, so I get up there, and for football practice, these players are having people trying to tackle them. They need to break through the tackles, and people trying to grab the ball. So they have this device that has these little concrete pylons that are about this far apart on springs. And then the players hold the ball, and they run through, and it's supposed to simulate getting hit by defenders. And hold on the ball and keep going. But it resists going through. And so that's what I think of for a resistor. It's something that you run through, and you've got to keep pushing. If you don't keep pushing, you're just going to stop. As a side note, having concrete pylons hitting you on the shoulder isn't happy. It really hurt. The players are wearing pads. I was not. But you live and you learn. So a resistor is resisting the electrons going through, and you have to keep working. You have to use energy to make them go through. And so the electrons, as they go through the resistor, they lose energy. Of course, how do we measure the energy of the electron? With the voltage, because the voltage is the potential energy per unit charge. And so the voltage is telling us about how much potential energy the electron has. As the electrons go through the resistor, that potential energy is doing work. For the resistors, it's making them hot. So the energy is being converted from the potential energy the electrons had into thermal energy, making the resistors hot. And so they're going to lose potential energy. That means they're going to lose voltage as they go through the resistor, which in this case is a light bulb. Light bulbs, by the way, an incandescent light bulb, the kind that is now outlawed for bulbs over, it's under 100 watts. I think you can no longer get incandescent light bulbs. Well, they can't make them. They can still sell their inventory. And it's because they're only 5% efficient at producing light. You make electricity go through that light bulb, and 5% of the energy that's absorbed by the resistor comes out as light. What do you suppose the other 95% is? It's heat. So they're really effective heaters, not very effective lighters. Here we have, actually, I'm not sure what kind of bulbs these are. I think they're fluorescents. Yeah. Out there in the hallway, they're not fluorescents. And in our offices, likewise, they're not fluorescents. They're, I think, low-pressure sodium vapor lamps, which when we get to light, it's easy to tell the difference when you have your little fun glasses we'll use. But those are about 30% efficient at producing light. Now, if you say 30% efficient at producing light, you don't feel very good about it, but that's 6 times better than an incandescent light. So it means it takes 6 times less energy to power these lights to get the same amount of light in the classroom. And you can see that would be a big savings in energy. Yeah.
What's the most efficient light?
For consumer purchases, it's about the same for LCD or LED or the fluorescents. LEDs are currently more expensive, but I don't think the LEDs, I think they're a better technology ultimately. As the price comes down, I want to shift my house from, I have compact fluorescents right now, to the LEDs. They're about the same efficiency, but I at least hope they're more reliable, because I don't know about you guys' experience with compact fluorescents. Mine might last a year and a half before they burn out. They say it lasts for 11 years. That's a straight up lie. It'll last 11 years if you're really, really, really lucky. So, yeah, it's pretty much the same between the two. They're both somewhere in the ballpark of 30%. And it varies by manufacturer, and there's a lot of variable there. Okay, so that's the electric circuit. The water circuit is here because it makes more sense to people initially. I get kind of frustrated with the water circuit, but with water, the elevation we talked about in class, the elevation is completely analogous to voltage. The higher the elevation for the water, the higher its gravitational potential. And so we have a pump that raises the water, hence raising its gravitational potential energy, or gravitational potential. And then the water goes down through a little turbine, and that turbine resists the water flowing through. So it's taking energy away from the water. Where's the energy going in the turbine? Well, hopefully it's to produce electricity. And then the water comes down to the lower tank, cycles around, so you don't gain or lose water in the circuit, you just move the water around. Now that don't gain or lose is an important part. Did you find this book yet?
I have not. No.
Try to find it before you leave. So, sorry, getting back to this, I just saw Yafet sitting down and it reminded me that somewhere in our setup we lost Paris' book. Make sure you did put it in your backpack, because you could have just put it there by habit. In an electric circuit, you don't use up electrons. You don't gain electrons. The electrons are just moving around the circuit. And so that's the analogy. And I went through and did some explanation about things like power, and I'm not going to go through the power here. I'm just going to stick with the electric circuits. Georg Ohm realized that for many materials, not all materials, but for many materials, the energy lost as charge goes through the material is proportional to the rate at which the charge is going through. And so Ohm came up with this equation that we call Ohm's Law right here. Now, I always have to interject. When I was in graduate school, I had a friend who had been in the military, and his job had been an electrician in the military. And he said, they tell us that we only have to memorize 3 laws and we can do anything with electricity. And these 3 laws are Ohm's 3 laws. And we said that's when I first started squinting a little, because there's only one Ohm's law. But here goes. Ohm's first law. V equals IR, where V is the voltage drop across a resistor. That's the difference between one side and the other side, the energy of the charge going in to the energy of the charge going out. I is the current going through the resistor. Notice the difference in the words. Voltage across, the difference between the top and bottom. Current through, going through. And R is the resistance. So that was Ohm's first law. And Ohm's second law was I equals V over R. And yes, then I laughed. And Ohm's third law and so what I took from this is, number one, probably they're not looking for the sharpest tools to be electricians in the military. But also, that really is a powerful equation. A lot of what we do in electronics, if you understand that, you can figure out what's going on. So that's what we're going to explore today. We're going to explore this equation. And specifically, we're going to check to see if it's true. So we are going to measure the current through a resistor and the voltage difference across the resistor and plot voltage on the vertical axis versus current on the horizontal. Now, I know if you turn that in, I'd take off points, right? Because you need to write out what it is and show the units. And you need a title to say what the purpose is. What's the purpose of the graph? The goal is truly to test Ohm's law, to see if it makes a correct prediction. So that's what I would put, graph to test Ohm's law. If you say graph to find resistance, that is appropriate because you are going to find it. If this equation here is true, if that's a correct equation, what should your graph look like?
Linear.
Should look linear. So there's step 1, should be linear. There is a second thing about what it looks like that you can pick out from that equation. What's the equation for a straight line? Y equals mx plus b. Which part of that are you missing in Ohm's law? Plus b. So what does that mean?
The y-intercept is 0.
That the y-intercept should be 0. So those are 2 predictions of Ohm's law that we're going to test and see. So it's actually, truthfully, very, very simple lab. To actually do the experiment takes a minute. Well, you have to do it twice, so there's 2 minutes. The setting up will take you a little bit longer. It took Yafet and me about 5 minutes, but I knew what I was doing. It'll take you much longer than that because you don't know what you're doing. But it's a quick experiment. That's why I don't feel bad about doing this lecture. we are going to make our measurements using a voltmeter and an ammeter. Voltmeter means it's measuring voltage. Ammeter means it's measuring current in units of amps. And this device here has both of them packed into one thing. So actually, I'll pull this out. These two connectors here are your voltmeter. And notice it says red plus. If you put it on something, it will measure a positive voltage if the red side is a higher voltage than the black side. So you need to pay attention to where you connect these to get the right sign for your voltage. Then here, where you have to put wires in, is the ammeter. And so the ammeter again has a plus and a minus. If current goes in the plus and comes out of the minus, it will measure positive. So you once again need to pay attention to direction or you'll get the wrong sign. Now a voltmeter, I already said voltage is measured across. So because voltage is measured across, if I have a resistor and I want to measure the voltage, where do I have to connect the two leads? One on each side. So my two leads go there, and in schematic form, a voltmeter is just a circle with a V in it. So that's how you connect it to measure voltage. But as soon as I connect that, I've created an alternate pathway. Some charge, instead of going through the resistor, could go through my voltmeter. And in fact, for most voltmeters, in order for them to work, that's what happens. The really expensive ones that are more accurate, they don't work that way. But for most of them, they do. So I'm going to have some current divert and go through the voltmeter, which means the current going through the resistor is a little bit smaller. If the current through the resistor is a little bit smaller, what's that going to do to the voltage drop across the resistor, according to Ohm? It's going to lower it. And so by the fact of connecting the voltmeter, I'm actually going to lower the voltage measurement a little. So of course, that's not ideal. Well, what would make it closer to ideal? Having more charge go through the voltmeter or less? Less. So how can we make less go through it? We make it a higher and higher resistance. So you can see I've highlighted up there that most ohm meters have resistances that are mega ohms to giga ohms. So if you're using, like in class today, we're using about 1 kilo ohm, about 1,000 ohms. If our ohm meter has a resistance that's a giga ohm, a billion ohms, 1,000 versus a billion, there's going to be virtually nothing that goes through the ohm meter, so it makes very, very small, like, 0.0001% difference. With our work, you know what? 0.0001%, not a problem. Ammeters, on the other hand, measuring current, I said measuring current, that's the current going through the resistor. So if I want to measure the current, here's my resistor, I need to put my ammeter right in line with the circuit. So all of the charge that goes through the resistor also goes through the ammeter. We call the ammeter connection a series connection. Series means that all the charge that goes through one has no choice but to go through the next. There's no other pathways. Parallel is what we call the voltmeter connection. That means the tops are connected together, the bottoms are connected together. The charge can go either way. So the ammeter has to be connected in series, which means if the ammeter has a resistance, there's going to be a voltage drop across the ammeter, which means less voltage drop across the resistor. Once again, you're changing the outcome. So in order to have the smallest change in the outcome, we want the ammeter to have the smallest possible resistance. So ammeters have very low resistance like less than an ohm. So they're pretty much the same as connecting a wire. What happens if you connect a wire between the two outputs of a plug in your home? Don't do this. What happens if you do that? Yeah, you have a big spark. You can weld. I've done it because some people aren't as smart as others. Okay, some people are smart. True story. When I was teaching PHYS, like my first year, we went out to Redwood Middle School, I think it is. And they were having a special science day, and I did some presentation. and they had a pastor give a devotional. And he was telling these kids, and we're talking kids from kindergarten up to 8th grade, about how when he was a kid, he loved to take coat hangers and put it in both sides of a socket. And I'm sitting back here, you can't tell kids that. Now, the truth is, one of these is grounded and perfectly safe. The other one is not and perfectly unsafe, potentially deadly. And so you could, if you stuck the one in the safe one first and then in the other one, you'd be safe. You just weld something and blow a fuse or circuit breaker. But if you go the other way, well, then you can end up bad things. And we will talk about electrical safety in class. It is important to understand electrical safety, to understand that we are using a voltage that, depending on how well grounded you are, may or may not be fatal. If you get up to 400 volts, that's about the most fatal voltage. If you go up higher, it'll stop your heart, but it's in a range where it'll just cause the heart to go into fibrillations, make it quiver and shake and do nothing. But we'll talk about that later. Now, because the ammeter has a very, very low resistor, you have to make sure you never connect the ammeter across the power supply. You can safely take a voltmeter and put the two ends of the voltmeter into the plug socket, provided you're not touching any wires, and measure voltage because they have really big resistances. But if you do that with the ammeter, you blow a fuse in the ammeter if you're lucky. If you're unlucky, you burn out the ammeter. So before you do your experiment, I'm going to have you call me over and I will check your circuit before you turn on any power to make sure that you have it connected correctly so we don't run into any problems because we don't want to damage these things. Okay. Talking about series and parallel. You have, for your hypothesis is really contrived, really fakeish. Because how many people actually look and see, oh, I saw they had resistors arranged like this? Only a few engineering students. Most people haven't seen it, so you're going to pretty much make up an observation that is not an everyday occurrence at all. Maybe something that's never happened in your life, probably. Your observation has to be about two resistors either connected in series or in parallel. And then your hypothesis, and so it's really simple once you decide is it series or parallel. Because your hypothesis needs to be, they did that because they wanted to make the resistance, and you have the options of go up, go down, or stay the same, because resistors in series/parallel do this. And then for your test, you're going to test to see what happens to the resistance when you put resistors in the way you observed. So your test is pretty prescribed. Your hypothesis is pretty prescribed. There's really only two options. Does everybody understand what I'm saying about the hypothesis and test? So I don't want people spending a half hour like, I don't get it. I'm not sure what he's looking for. Right? There's only two options there. So series, as I said earlier, they're all connected one to another. So if I have current flowing, current that goes through resistor 1 has no other pathway but to continue going through resistor 2 and so on. So those are connected in series. Parallel, I have current that comes in here and it can split and go this way or this way or this way or this way. But then it all has to come back together in the end. So parallel, you have multiple pathways between the starting and ending points. The tops are all connected together, the bottoms are all connected together, and the charge has multiple pathways that it could go through. So that's the difference in series and parallel. Now, if you have things in series, you lose energy going through the first one, then what happens with the second? You lose more, and you lose more. So what's going to happen to the voltage drop across the entire thing as you go through multiple resistors in series? It's going to be adding up, so it's going to get bigger and bigger. Now, if you have them in parallel, you could go through one, or you could go through another, or another, or another. Each one's only going to get a portion of the current. So the current going through each one is smaller than the total current. What's that going to do to the voltage drop? It would be the same as if you had just one of the one resistance with a certain amount. but the voltage drop is going to be smaller than the smallest voltage drop you would have had because the current is split up through all of them. So when you put them in parallel, you're actually lowering the resistance, and this is where the water idea comes in. If we look at that water analogy, if I put another pipe in parallel, so if I just put another pipe here, and I'm going to make this pipe just a skinny pipe so it's going to resist some flow. Is water going to go through the turbine if I have that other pipe there? The water doesn't freely flow through the other pipe because it's kind of narrow. So is it going to flow through both or just one? It's going to flow through both. But what's going to happen to the amount of water that flows through the turbine? It's less because you have it splitting between the two pathways. And so the total current is split between two things, and the actual amount going through one is smaller, hence the voltage is smaller. Now let's work out the equations for how resistors add in series and parallel. We worked out in class yesterday how capacitors add in series and parallel. You remember that, right? Everybody's got that long of rememory. We all remember words like that, rememory. So let's just look at the work for how it happens. So here's 3 resistors in series. So this is a series combination. And what I want to do is take this circuit with 3 resistors in series and compare it to what resistance is equivalent to those 3. So what single resistance would have the same end result as those 3 resistors combined. So a symbol. That E stands for electromotive force, which is a totally anachronistic term. It's not correct. There used to be a theory that a battery was applying a force to electrons to give them energy. And so they talked about the electromotive force as something about the force being applied to electrons. Well, as we've come to understand, it's a whole chemical reaction. There's no actual force pushing electrons through the battery, but we still use that term electromotive force and use that script symbol EMF. So that electromotive force is the terminal voltage of the battery. Actually, it's only terminal voltage if it's an ideal battery, so I'm just going to put voltage of battery. And I'll talk in class tomorrow about the difference in terminal voltage and the voltage of the battery. So that's what the EMF is. So I'm going to have the same battery, hence the same voltage. And if it's equivalent, I'm going to have the same current. So same current and same total voltage. Now you told me, how does the voltage of resistor 1, resistor 2, resistor 3 relate to the total voltage? You already told me. What, Jordan?
Equal.
Okay, equal to, say it more clearly.
The total is equal to, or the initial minus what the resistors have been.
Okay, the total is equal to the sum of each individual resistor. Did you check in your backpack to make sure it wasn't there? And it wasn't. So what we're going to have is the EMF is equal to V1 plus V2 plus V3 is equal to I times R1 plus I times R2 plus I times R3. What did I do in that second line? I just used Ohm's Law. They all have the same current I because they're in series, and series has to have the same current. Now over here, I have the EMF is equal to I times the equivalent resistance. Well, if it's the same EMF and the same current, I set these two equal to each other, and I end up with IR series is equal to IR1 plus IR2 plus IR3. And as I said yesterday, we are all plenty smart enough to realize we can cancel the I, and we have R series is equal to R1 plus R2 plus R3. So resistors in series simply add algebraically, the simplest way to add, right? Well, except for saying it's 0 every time, I suppose. Why do they add algebraically? Because the total voltage is equal to the sum of the individual voltages, and they all have the same current. Now let's go to parallel. In parallel, I again have a current coming out of here. But in parallel, what's going to happen to that current? It's split, so I'm going to have separate I1, I2, and I3. So each resistor has a different current, but because they're in parallel, the tops are all connected together, the bottoms are connected together, and the voltage across them is the difference between top and bottom. So the voltage has to be the same for each one. So because they're in parallel, I'm going to have V1 equals V2 equals V3 equals the EMF, which means I can calculate the currents. I have the total current is split up 3 ways. If I have electrons, let's say I start with 100 electrons and 50 go in the first pathway and 30 go in the second, how many go in the third? 20, right? Because you know the electrons aren't being created or destroyed, they have to go through. So since current is charge per second, the current has to add up. So I have to have I equals I1 plus I2 plus I3. But using Ohm's law, Ohm's second law, I is V over R, and so this is equal to V, or the EMF over R1 plus the EMF over R2 plus the EMF over R3. Now, if we look at the equivalent circuit, we have the current is equal to the EMF over the R parallel. So once again, just like last time, set those equal to each other. You have the EMF over R parallel plus EMF over R1 plus EMF over R2 plus EMF over R3, which canceling out the EMF since it's in every term. Now, I want to point out one last thing before we get to starting the experiment. That one last thing is you will often see an equation for parallel resistors that looks like this. How many people have seen that equation? All of my electronics students. This is perfectly correct if you only have 2 resistors. Why? Because if you have 2 resistors, the full equation, 1 over R parallel, is equal to 1 over R1 plus 1 over R2. And so you invert everything, so you're going to have 1 over RP is equal to 1 over R1 plus 1 over R2. Now, what's 1 over R parallel? R parallel. So this becomes R parallel is equal to, and then to simplify, we multiply both top and bottom of the right side by R1, R2. Right, multiply top and bottom by the same thing so it doesn't change anything. But then I can have my R1s cancel, my R2s cancel, and this is that equation. So it works perfectly if you have 2 resistors. But what if you had 3 resistors? If you do the same work, you're going to end up with RP is equal to, you're going to have to multiply by R1 times R2 times R3. And the 1 over R1 is going to cancel the R1, leaving R2, R3. The 1 over R2 is going to cancel the 2, leaving R1, R3. And then the R3 leaves R1, R2. And nobody ever writes it that way, right? Because it's getting longer and more convoluted. And so that's why I work it out with 3. So you see the equation that If you had a fourth one, you just play, put 1 plus 1 over R4 plus 1 over R5, etc. And it always works. Any questions about the series parallel? Yes, Aaron.
So is it true that the total resistance for a parallel circuit is always less than any one of the individual ones?
Yes, it is. Now that we have this equation, we can show why. You have 1 over R parallel is equal to the sum of these, right? So if I take these 1 over R1, 1 over R2, 1 over R3, when I add them together, I'm going to get a bigger number, right? So let's say R1 was the smallest value of all my resistances. So 1 over R1 is a big value, right? But then I have 1 over R2. R2 is a bigger value. So that's a smaller, but I'm going to add it. And so when I add all of the 1 over R's, it's a bigger number than the biggest 1 over R by itself. Which means when I invert, it's a smaller number. So it has to always be, when you have them in parallel, the total resistance is always less than the smallest of all of your resistors. Whereas when you put them in series, the total resistance is always bigger than the biggest of all your resistors. Any other questions?
Can you pretty easily use that equation plus like the resistance that you have in your voltmeter to calculate the percent error of the voltmeter?
Yes, you can. If you know what the resistance of the voltmeter is, yes.
Okay.
Any other questions? All right, then let's get to how we're doing the experiment. You're going to grab a resistor. So where are the resistors? They're right here. Come grab one. Pay attention to the colors. If you look at these resistors, you see that they have color bands. So this one here, it's gold on one side and brown on the other. Ideally, one band is closer to the edge than the other band is to its edge, and you start with the one that's closer to an edge. But this is pretty symmetric. But there's another thing. We have the color code, and the first 3 bands are going to be black, brown, red, orange, yellow, green, blue, violet, gray, or white. The last band is going to be gold or silver. And so since this has gold on one side, I know that's the bottom. And so I take this, and the colors on this one are brown, I think that's gray, got to pay attention, red, and gold. So if it's, being my age, these days, I would take a picture with my phone and use that to identify what the color really is. Because you know how it is, you get old and your eyesight not as cute as it used to be. So with the one I have here, to the best of my ability, yeah, that doesn't work at all. Yeah, that's not working. I think it's brown gray. And what did I say the third one was? Black?
Red.
No, yeah, red. Had to have been red.
Gold.
Each one of these corresponds to a number. So I look at this table right here and I say brown corresponds to 1, gray corresponds to 8, red corresponds to 2, and gold corresponds to 5%. The last one is the tolerance. It tells you how accurate you are. The first 2 are just normal numbers. So the first 2 numbers together give me 18. The third one, 10 raised to that power. So the way I read this is 18 times 10 to the second plus or minus 5%. So this here was what red told me. And then, of course, the 1 and 8 are clear. So you're going to need to make sure you pay attention to the colors. For your test, you're going to have to grab a second resistor. Make sure your second resistor does not have the same color code. Right? It needs to be a different color code. So you need to write down the color code. For step question comment 2, you need to write down the color code, convert it into the nominal resistance. Nominal resistance means in name. So that resistor is 1800 ohms. I didn't put the units here, I should have. So it's 1800 ohms plus or minus 5%. So we don't know exactly what it is, but it should be within that range, unless somebody's abused. If somebody's cooked it, right, these are quarter watt resistors. If somebody's like put half a watt of power through it, well, then it may not be so accurate anymore. What is power? Power is the energy per time, right? And so voltage is the energy per coulomb, and current is the rate the coulombs are passing, coulombs per second. So power is just voltage times current. So that's how you can know what the power is going through something. Okay, so for question 2, you're going to write down the color code and calculate what the nominal value is. For step 3, I'm going to bring out a multimeter. You'll just take the resistor away from everything, connect it to the multimeter, and it's a device that measures the resistance. So you're going to do that with a multimeter. So I'll have to get out a multimeter for that. Question 1 is about your graph, and you need to have 2 reasons why your graph agrees with Ohm's Law, right? Why it supports Ohm's Law. We've already gone through those, so now let's do the actual experiment. The actual experiment starts with really simple, how to make your diagram. What's the symbol on the left there of the 2 symbols? It's a battery. How do you know that the top is positive? The longer side. Okay, the one on the right is a resistor. And with a resistor, you do need to try to make those straight lines, because if you curve them, that becomes an inductor. So you do need to try to make them straight lines because there's something similar. And the first thing you do is you say, how would I make this into a circuit? So what was the rule for a circuit? It has to start where it ends. So you have to use wires to make it start where it ends. That's really simple, right? I'm pretty sure everyone sees that instantly, right? Then the second thing you have to do is start again and put your ammeter and your voltmeter in, so you're measuring both at the same time. How is an ammeter connected? In series. How is a voltmeter connected? Parallel. You'll find there is not a perfect answer for the second one. There are 2 equivalent. Neither one is perfect because of the resistance of an ohm meter and the resistance of an ammeter. So you can choose either one of the 2 not quite perfect options. So you draw that diagram, then you're going to make a circuit that matches your diagram. So to make the circuit, I made half a circuit here, and I'm going to remake only half the circuit because I want you to learn what you're doing. But to make the circuit, I start with wires. Red wire for positive, black wire for negative. And I plug them into the outputs here. And the first thing I'm going to do is connect my circuit as we had for the first one to make a complete circuit. So I'm going to take my resistor and just clip it, make sure it's actually making connection, clip it in there, and I have the resistor now making a complete circuit. Not hard, right? Now I'm going to connect only the voltmeter. So when you connect the voltmeter, how's the voltmeter connected? Okay, the voltmeter is connected in parallel, one before and one after. Which side should I have the positive of my voltmeter on? On the side that I have the positive from the power supply. To do that, I just shove it in, right? They plug in together. You don't have to have anything special. Last year I had some students, I didn't make this clear, and they were trying to, use clips to hold multiple plugs together. They just slide in. So now I have my voltmeter connected. Like I said, I'm not going to connect the ammeter mostly because I just don't want to show you what the data is going to be. It's simple. I just don't want to give everything away. So I have half the circuit connected. I made it so it matches my picture. Now I need to take my data. And this is where things get oh so easy. So make sure I have, that looks right. I have the signal generator I need to see. So you saw where that signal generator tab is? You need to have that open. Well, I kind of would like to see my numbers. If I click this little red thumbtack, it'll show me my numbers and make a smaller display so I can't read jack. or I can turn it off and I'll see my graph but not see the numbers. I'm going to choose to do it where I can't see the numbers but I can see the graph. So I'm ready to take data. To take data, hit preview. And now you can see the numbers there. It's 0 volts. See the 0 right here? 0 volts DC. When I think I have what looks like good data, actually, yeah, stop. I want to do something here. I totally missed stop apparently. There we go. Okay, it doesn't have something it had before. I'll not worry about it. Okay, so go back to preview. When I think I have good data, I hit keep sample. And then it'll be easier for you than me because I have to use my pen to do this. I raise the voltage by 1. See, I tapped the little up button and it went up to 1 volt. And then I click keep sample. And then I raise it to 2, keep sample. Raise it to, whoops, that was down. Raise it to 3, keep sample. Raise it to 4, keep sample. Get the picture? And so I keep raising it until I have a total of 10 data points. I'm not going to go to 10 because, of course, my data here is meaningless because I don't have the ammeter connected. Now, you can see here a problem. Look at that data. If the ammeter is not connected, what should the current have been? Should have been 0. Now, there is a way to correct that. If I go to, I think, the data, the output current, somewhere here it has an option to reset. I think that, oh no, reset the errors. My bad. That didn't reset what I thought it did. I think there's a way to 0 it. Maybe in calibration. That brings up the same thing. Great. Okay, not going to worry about it. We just won't worry about that. But you can see that there is an error there in the current measurement. The current, if you look at the values, you'll see that they jump by 0.5 milliamp. So what's your uncertainty in current going to be? 0.5 milliamp, because it jumps by 0.5 milliamp. So that's an easy given for the uncertainty in the current. The voltage is much less uncertainty. This does a fit. Do I care about all of this negative space? No. So I'm going to just do the auto fit first. Didn't do much good for me. Fit it manually so I have 0, 0. And adjust my scale. Okay, because all my lines vertical data, it's not very useful. But make sure you frame the data well so you don't have empty space. Make sure you don't have your slope and y-intercept information on top of your line. And then take a snapshot of just this graph. How do you make it just that graph? I will show you. You click there on the little arrow beside the camera, choose the bottom option, and that's going to then show only one of the displays. Make sure the graph is the one that has the little dots around the edges. Then you click the center of the camera, and there you can see I took a picture of just my graph. It calculates the slope and y-intercept for you, so you don't have to do those calculations. You will want to, save it to PDF, including your lab report, of course. You're done with the experiment at that point, except for you're testing your hypothesis. How are you testing your hypothesis? Depending on if you chose series or parallel, you're going to take a second resistor. Remember, the color code needs to be different, and you need to go through the same steps of determining what the resistance is for this. And if I chose to do parallel, I'm just going to double up here, which my calculus teacher in graduate school, that was how he said to develop, and I did not know. I thought he was telling us to double up a theory. I couldn't figure out what it means to double up a theory. It was develop. So here I have the two in parallel, and then I'll go through and repeat the experiment to find out what the resistance is for two in parallel. If I did series, it's one step more complicated. I need to get another clip so I can put them in series. Yeah. And it works better if you have a partner with you. Okay, so there I have them held in series, and I repeat the experiment. So it's going to take another minute to do the hypothesis test. You saw how quick the test goes, right? You can see you can do it in a minute, right? Okay, good question.
That is for our portion, then you want us to run the graph again for our.
Yes. Yeah. Question here.
Is color code enough for like saying what the individual resistances are?
No, also use the multimeter.
For our own experiment? Okay.
Yeah. You don't have to do another one with this to get through this, but you do need to do the color code and the ohm meter. Yes?
Do you have to go through and like re-answer the questions again when you do it, or?
No. Except for, like I said, you do need to do the color code and the actual measurement of the resistance, which is actually 2 of the 4. But any other questions? Okay, go ahead and get started. I have your equipment. Remember, before you actually start turning on power and taking data, I want to check your circuit just to make sure you don't accidentally put your ammeter across the power supply.